Hey everyone, so you're gearing up for that Unity certification exam. It's not just about what you can build. It's about really truly understanding the deep kind of hidden rules of the engine. In this explainer, we're going to dive deep into those critical APIs that control object life, game time, and math. The exact stuff that trips up even good developers on the exam.
So let's just start with this question right here. What is the real difference between a developer who's good and one who's certified? It's actually not about writing the most complex code or the fanciest shaders.
It all comes down to this, knowing the hidden rules. It's about understanding those subtle, sometimes weird APIs that control how the engine really works under the hood. Getting a handle on these tricky concepts is the absolute key to crushing that certification exam. So, let's get into it.
All right, here's our game plan. We're going to start with how objects are born and how they die. Then we'll get into mastering game time with coroutines. After that, we'll tackle the super confusing activation paradox. Figure out why your math sometimes just fails, and then we'll wrap it all up with a little quiz to make sure it all sticks.
First up, the object lifecycle. This is all about spawning things into our world and, just as important, getting rid of them the right way.
And the heart of all this is the instantiate command. Anytime you see a bullet fly out of a gun, an enemy pop into existence, or an explosion effect, that's instantiate doing its job. It's the factory for everything that doesn't start in your scene from the get-go. But here's the thing, not all instantiate calls are created equal. The basic one just, makes a copy. The one with position and rotation, that's your go-to for spawning something right where you want it, like a particle effect. But I really want you to look at that middle one, the one that takes a parent. This is a huge exam tip, especially for UI. If you spawn a UI element and then parent it, Unity has to do all these expensive calculations twice. But if you do it all in one go with this overload, it's way, way faster. The exam loves to test you on little optimization details just like this one.
Now let's talk about the other side of things, destruction. And this right here is one of the biggest, most common traps on the entire exam. When you call destroy, your brain thinks the object is just gone, vanished, poof. But that is not what's happening.
Let's actually look at what happens inside a single frame of your game. You've got your update methods, your late update methods, then the rendering happens, and only after all of that is finished, right at the very, very end of the frame, does Unity finally get around to actually deleting the objects you told it to.
And this is the key takeaway, the thing you have to burn into your brain. If you call destroy on an object, and then on the very next line of code you try to access it, maybe to get its name or check its position, it will work. It's still there. The object is just marked for deletion, but it sticks around in memory for the rest of that frame. Trust me, you will see this on the test.
This whole idea of things happening at specific points in the frame, it leads us perfectly into our next topic, mastering game time. Sometimes you need your code to just wait, but without freezing the whole game. And for that, we have coroutines. They're Unity's secret weapon for asynchronous stuff.
Okay, this slide right here is probably one of the most important distinctions you need to know for the exam. WaitForSeconds, it's tied to the game clock. So if you pause your game, set time.timescale to 0, this timer stops too. It's perfect for something like a player stun effect. But WaitForSeconds real time, that uses the actual real-world clock. It totally ignores time.timescale, so it'll just keep on counting down even if your game is paused.
And then there's this little guy you'll see everywhere, yield return null. It's the simplest instruction you can give a coroutine. All it says is, hey, pause what you're doing, let the engine run for one frame, and then come back and continue right where you left off. It's awesome for stuff that needs to happen over time, like smoothly fading a UI element in or out.
All right, next section. The activation paradox. This is a big one. Just because you look in the inspector and see that little checkbox ticked for an object doesn't actually mean it's running or even visible in your game. This whole area is a huge point of confusion, and the exam loves to test it.
The best way to get this is with an analogy. Think of activeSelf like the little switch on a lamp. It just tells you if that one lamp is turned on. But activeInHierarchy, that's like the main circuit breaker for the whole house. If that breaker's off, it doesn't matter one bit if the lamp switch is on. There's no power. An object is only active in the hierarchy if its own little checkbox is ticked and every single one of its parents all the way up the chain are also ticked.
And that leads us to this critical rule. If an object is inactive in the hierarchy because one of its parents is turned off, its scripts are completely asleep. They're dormant.
Update doesn't run, fixed update doesn't run, nothing runs. The object is basically offline until its entire family tree gets woken back up.
Okay, for our last big topic before the quiz, let's talk about math. Specifically, why your math sometimes gives you really weird, unexpected answers, and the awesome helper functions Unity gives us to avoid those bugs.
So, take a look at this. In normal human math, this seems totally obvious, right? 1 is equal to 3 times a third. Super simple. But what does a computer think about this?
Take a second. What's your gut feeling? Is this statement true or is it false? Go on, lock in your answer.
The answer is, almost every single time, false. And it's because of a weird thing called floating point imprecision. See, computers are bad at storing decimal numbers perfectly. So a number like 1/3 ends up being stored as something like 0.33333. And when you multiply that by 3, you get 0.9999, not a perfect 1.0. That tiny difference makes a direct comparison fail.
So what's the big takeaway? Never, ever, ever use the double equal sign to compare float values. Instead, you use this hero of a function, mathf.approximately. It doesn't check if they're exactly equal, it just checks if they're, close enough to be considered the same. This is the professional, bug-free way to handle it.
And while we're talking math, there are two other workhorses you have to know: lerp and clamp. Lerp is your best friend for smoothly moving from one value to another over time. Think fading in music or moving a camera. And clamp is just awesome for making sure a value stays in a certain range, like keeping a health bar from going below 0 or above 100.
Okay, you've learned the rules, you've seen the traps. Now it's time to put it all to the test. Let's do a quick final challenge with a few questions that feel like they're ripped straight out of the real exam.
Question number 1. You have a stored object, and its little active checkbox is ticked, but it's the child of a parent object that's turned off. A script on the sword tries to log a message in update. What shows up in the console? The answer is D. Nothing is printed. That's the activation trap. Because its parent is off, the sword isn't active in the hierarchy, so its update method never, ever run.
Okay, question 2. You call destroy on an object, and then on the very next line you try to debug.log its name. What happens? Do you get a big scary error? Nope. The answer is B. The name gets logged just fine. Remember, the object is only marked for deletion. It doesn't actually get wiped from memory until the end of the frame.
And our final question. You're coding a stun effect that needs to last for 2 seconds. But, crucially, it has to pause when the player hits the pause button. Which command do you use inside your coroutine? The correct answer is B. WaitForSeconds. Because it respects the game's timescale, it will automatically stop its countdown when you pause the game.
And we are done. We've hit lifecycle, timing, activation, and math. All those sneaky little rules that the engine runs on. So the last question is actually for you. Now that you know about all these hidden traps, which float comparison or destroy call or UI instantiation in your own project are you going to go back and fix first? Thanks for watching.